Dear students, in this lecture we discuss some basics of multivariable calculus. We are going to discuss scalar and vector fields. So we stick to real vector spaces. So first let us see what is meant by Rn. So this R denotes the set of all real numbers. R2 is cross product of R with itself. It is also a plane. This contains all the order pairs of the form x comma y such that x and y both are real numbers. So this is nothing but our usual xy plane. This is origin and say this is 1. So this is -2, then this point is order pair 1 minus 2. Okay, so this is familiar to us. Similarly, we have R3, that is space. It is order triples R cross R cross R, and that is set of all triples x, y, z such that x, y, and z are real numbers. And this is as usual space. Okay, x, y, z. In general, we will have Rn. And this n is natural numbers 1, 2, 3, etc. Now we consider the functions f from Rn to Rm. So domain is n-dimensional real space and values are in Rm. So here, first thing, if n equal to m equal to 1, then this f is a real valued function of real variables. A real valued function of real variable. Second thing, if n greater than 1 and m equal to 1, that means domain is higher dimensional but values are in one dimension, okay, in R. Then F is called a scalar field. Third case, if m greater than 1, then we call this as vector field. Next thing is some properties of vectors. So elements of Rn when n greater than 1 are called vectors. Elements of Rn with n greater than 1 are called vectors. We denote them by using bar. For example, x bar equal to 0 minus 3 in R2. Next thing is dot product of two vectors. Let x given by x1, x2 and so on, xn, and y given by y1, y2 and so on, yn are vectors in Rn. Then, sorry, I should write here. If x and y are vectors in Rn, then we define the dot product. It is also called as inner product of x and y. We may call them as x bar, y bar, x bar and y bar, as x bar dot y bar equal to summation xj multiplied by yj, j equal to 1 to n. Okay, so this xj multiplied by yj is usual multiplication in reals. Second thing is norm. Norm of a vector. If x bar equal to x1, x2, and so on, xn is vector in Rn, then norm of x bar is defined as, so this is symbol norm of x bar, and that is equal to square root of x1 square plus x2 square plus and so on plus xn square. It is nothing but square root of x bar dot x bar. So dot product of x bar with itself, its square root. Okay. Note that norm of x bar is distance of x, the point x bar in Rn from origin. Distance of x bar in Rn from origin in Rn. Okay. Next, we define Jacobian matrix of a function. So here, for simplicity, we may consider R2 or R3. Let us see. Consider our f from, say, Rn to Rn. So its values are in Rn. Okay. So let us take n equal to 3. Therefore, we can write f of, so here f is from R3 to R3. So domain variables are, say, small x, small y, and small z equal to, say, f1 of xyz, comma, f2 of xyz, and f3 of xyz. So these f1, f2, and f3 are called components of capital F. Okay. These functions f1, f2, and f3 are called components or Euclidean coordinates. Component functions or Euclidean coordinate functions. Of this capital F. if we write I hat equal to 1 0 0, J hat equal to 0 1 0, and K hat equal to 0 0 1, that is unit vectors in R3. Unit vector means vectors with length 1, and these are orthogonal to each other. Orthogonal means these are making angle of 90 degrees with each other. Okay. So mutually orthogonal unit vectors. Then we may write capital F equal to F1 I hat plus F2 J hat plus F3 K hat. Okay. So this one. So it is F1 of XYZ into 1 0 0 plus F2 of XYZ into 0 1 0 plus F3 XYZ into 0 0 1. Okay. So it is like this. We define the Jacobian matrix of F as df at xyz equal to, it is matrix whose first row consists of partial derivatives of f1. Okay, so partial derivative of f1 with respect to x. Then second entry is partial derivative of f1 with respect to variable y, and third entry is partial derivative of f1 with respect to variable z. Okay, so in first row we consider partial derivatives of this coordinate f1 with respect to x, y, and z. Similarly, second row will be for f2 and third row for f3. So partial f2 with respect to x, partial f2 with respect to y, and partial f3 with respect to z. I should say f2. Sorry. Second row is for f2. And third row is for f3. I hope you are familiar with partial derivatives. Otherwise, I am explaining here. We call this partial f1 with respect to x is partial derivative of function. Of course, it is a real value function. Function f1 with respect to, in short, we will write WRT hereafter, okay, with respect to variable x. And how to find such derivative? In this case, we treat all other things constant except x. Okay. In this computation, we treat all other variables constant except okay. For example, if my f1 of xyz equal to x square y plus xyz plus 3yz, then this partial derivative of f1 with respect to x, this partial f1 with respect to x is on right hand side of f1. Now we consider x as a variable and all other means y and z as constants. Okay. So with respect to x means here it is some constant multiplied by x square. So it should be 2 times x and this constant y. Here it is y into z only. Okay, derivative of x is 1. So plus yz, and here x is absent. So derivative of this is 0. We are treating all other things constant except x. So it is 0. Okay. Similarly, we can have partial f1 with respect to y. So it is here in first term it is x square, in second term it is xz, and in third term it is 3z. Okay. And partial f1 with respect to z, it is here z is absent, so 0. Here it is some constant into z, so it is that constant means xy, and here it is plus 3y. Okay, so these are partial derivatives. So this is Jacobian matrix. If our function is from R2 to R2, then also we can have 2 by 2 Jacobian matrix. Okay. Note, if we have f from R2 to R2 with f of xy equal to f1 of xy, f2 of xy, and that can be written as f1 of xy into I hat plus f2 of xy into j hat, where I hat is unit coordinate vector 1, 0, j hat is unit coordinate vector 0, 1 in R2, and that is nothing but I hat is along x axis and j hat is along y axis. We can sketch here. So I hat is 1, 0 means this point is 1, 0. We show this by arrow. So this is vector along x axis starting at origin and up to point 1, 0, that is of length 1. This is I hat, and we have j hat that is along y axis. Okay, so this is z hat 0, 1. Okay, so from origin to point 0. Then the Jacobian matrix of f is df of xy, which is 2 by 2 matrix. First row is del f1, partial f1 with respect to x. Second entry in first row is partial f1 with respect to y, and second row is for f2. Okay. Next concept is curl. curl of a vector field. Okay. Before that, we need basic thing about cross product of two vectors. Let me discuss the cross product and then we can have curl. Cross product of two vectors. Let us consider vectors in R3. It can be discussed for R2 also, that doesn't matter. V1, I should say V bar. Let V bar given by, say, V1, V2, V3, and W bar given by W1, W2, W3 be vectors in R3. Okay. The cross product of V bar and W bar denoted by V bar cross W bar is defined as the vector V bar cross W bar equal. So it is determinant whose first row is unit coordinate vectors I hat, J hat, and K hat. Second row is coordinates of V bar, that is V1, V2, V3, and third row is coordinates of W bar, that is W1, W2, W. Okay. So we can simplify this. It is I hat into, okay, so this determinant, so it is V2 W3 minus W2 V3 minus J hat. Okay, this is the determinant of 3 by 3 matrix minus J hat into V1 W3 minus W1 V3 plus K hat into V1 W2 minus W1 V2. Okay. This is cross product of two vectors and it is again a vector in R3. We already discussed dot product. Okay. Similarly, if we have vectors in R2, then cross product, suppose V bar is given by V1, V2, W bar is given by W1, W2, then the cross product will be when we have R2, we don't take this cross product because This cross product is a vector which is perpendicular to both v bar and w bar. Okay, so if we are in plane, then we can't have something which is perpendicular to both vectors in that plane. Okay, so here, if we consider v bar and w bar in R3, then we can define this cross product and note that v bar cross w bar is perpendicular to both v bar and w bar. Next, we are ready to define curve of vector field. So we consider vector field in R3. The curve of a vector field. So consider the vector field consider differentiable vector field means each component of that vector field is a differentiable function. F of xyz equal to its coordinate functions are p, q, and r. P of xyz into I hat plus q of xyz into z hat plus r of xyz into k. Okay. The curl of F is another vector field given by so notation is curl F equal is partial derivative of r with respect to y minus partial derivative of q with respect to z into I hat plus partial derivative of p with respect to z minus partial derivative of r with respect to x into z hat plus partial derivative of q with respect to x minus partial derivative of p with respect to y into k hat. Okay. So when we consider the first term, that is coefficient of I hat, it is partial derivatives of second and third components with respect to y and z. Okay. When we consider z hat, then derivatives of first and third components. Okay. With respect to z and x. Okay. And when we consider coefficient of k hat, then we take derivatives of other two functions, p and q. Here order is qp, okay, and we are differentiating with respect to x and y. Okay. So there is another way to obtain this curve. Let us see. If we define the operator del, which is equal to, whose components are partial derivative operators. First component is partial derivative with respect to x, second one is with respect to y, and third one is with respect to z. Or we may write this as partial with respect to x I hat plus partial with respect to y z hat and partial with respect to z k hat. Okay, so this will operate on some yield. Okay, so what is del cross f? Then this operator cross product with f, by definition of cross product, it is determinant whose first row is I hat, j hat, k hat. Second row is components of this del. These are partials with respect to x, y, and z. And third thing is components of f. These are p, q, and r. Let us find this determinant. It is I hat into this determinant, that is, okay, so partial derivative of r with respect to y minus partial derivative of q with respect to z into I hat, then minus this thing, that is partial derivative of r with respect to x minus partial derivative of p with respect to z into z hat, and third component is this determinant, that is partial derivative of q with respect to x minus partial derivative of p with respect to y into k hat. Okay, we can absorb this minus sign inside the bracket and we get the same thing which is here. Okay, so coefficient of I hat is partial r with respect to y and q with respect to z. Okay, then second, if we absorb this minus sign inside, then it is partial p with respect to z minus partial r with respect to x. Okay, and third thing is q with respect to x and p with respect to y. So this is same as curl. Okay, so our result is therefore curl f is nothing but del cross f. We discuss some more terminologies in the next lecture, that is divergence of vector field. Then we solve some examples and we discuss gradient of scalar field.